Hello, Eigen family.
Welcome.
Welcome back, guys. Make sure you like, share, comment, subscribe as you normally do. And, guys, make sure you also check out the website, Eigenbros.com, Eigenbros on Twitter, Eigenbros on Instagram, Eigenbros2 on TikTok. And then, guys, thank you, patrons, once again. We
Seriously,
greatly appreciate you.
thank you. Thank you for all the new patrons, too.
Yes.
And thank you for sticking through us
Yeah.
through this very difficult time.
Yeah, me and Juan are a little tired.
Yeah.
Juan's been working. It's kind of later. You guys probably notice the lighting is a little bit more, what is it called?
Violent?
A little more, no, not violent, a little more subdued.
Subdued? You think it's
Yeah.
milk toast? This ain't.
I don't know about milk toast. I don't know what that means, but
It's, well, not too. It's in the middle. It's like,
Yeah.
lukewarm.
But yeah, guys, patrons, thank you guys so much. And if you want to be a Patreon member, check out patreon.com/Eigenbros. And then also with that, you'll get the 30-minute audio podcast. And then also you get access to Discord. So, guys, check it out. $1.
Chat with us directly or the community, and you
Yes.
can ask us anything. And most people ask us for
Money.
because we've been through the ringer. We've been through the whole graduate career, and so if you want our experience and any, we're gatekeeping this knowledge
Behind a paywall.
behind a paywall.
Your boys have sold out.
It's an access fee, but I mean, for the price of a pumpkin spice latte, if it's in the season, so get one of those. For the price of one cup of coffee, you get to support us.
All right, let's stop begging now.
Anyway.
Let's get to the goddamn episode.
Yeah. Anyway, this episode is actually. I asked Terrence to do the heavy lifting this week.
Yes.
Yeah.
Well, this is my time to be able to do it. So we'll do it. Let's do it.
Yeah.
I mean, it's a cool one. The Nobel Prize, pretty interesting. Always a fun one to tackle. When you're when it happens, because everybody's wondering who the hell's going to win it and why, and you want to see, are they justified in getting it?
Yeah.
Whatever. And
How
much did you get to look into it? One, do you know the names of the guys who won at
I
least?
do. The names are, and I have a nice little infographic.
I always like the little Nobel Prize artwork they got.
Yeah. I have it pulled up. This one.
Yeah, you got it. That's it.
Yeah, this is the Nobel Prize in Physics was given by, actually, shout out to the illustrator, Niklas Elmehed.
I wonder if he's on Twitter.
Niklas.
Hopefully we can
Elmehed.
insert his
Yeah,
Twitter
yeah,
if we find it.
Yeah, we'll go ahead and put it in there. But the Nobel Prize in Physics is awarded by the Royal Swedish Academy of Sciences, for those of you that don't know. And it was given to 3 scientists.
They've been doing a lot of threes lately,
Have
if
they?
you've noticed. Yeah, because the last one was threes. Remember the gravitational waves with the Kip Thorne and the other guys? That was
Oh, true.
threes. They've been doing a lot of threes, which is interesting. I'm not sure why. I guess they're just trying to recognize more of the collaborative effort of science, which I think is legit.
The comedy rule of threes?
I don't know how much comedy's in the Nobel Prize, but
No, yeah, I think you're right about that. I think the 3 is probably more to highlight,
Representative.
maybe similar contributions or impacts.
yeah, I think so. Because you remember
Yeah.
the last one was the Penrose, and he had
Yeah.
3. There were 3 as well there.
Yeah.
There's always kind of a stellar person who stands out, though. And the 3 names on this one, I think, are Hasselmann, a German. I think he's from the Max Planck Institute. There's
Klaus. His name's Klaus,
Syukuro.
right?
Yep.
Yeah, and then Saikudo Manabe.
Yeah, Manabe. Yeah.
Oh,
He's from the U.S. I think he's from Princeton.
Hey, would not surprise me.
Did they say his school name?
No.
I don't want to fuck that up, so don't take that.
Well, it just says that
not
they
sure.
both won the award, Manabe and Hasselmann, for the physical modeling of Earth's climate, quantifying variability and reliably predicting global warming.
Right. So this has to do with complex systems and chaotic systems and whatnot. And then, of course, the third guy is the one that kind of shines the most to me. Because, of course, huh?
Sorry, we're going to put the image up again, but if you see the image, They literally have him facing the other way.
Ooh, is there some kind of mystery to that?
The subtext there is that he
stands alone.
He stands alone.
Well, he is the one. He gets half the prize himself, and the other two guys, I guess, get a quarter each.
Oh, okay.
Apparently. Okay. So I guess that's how they distribute the money as well. Mm-hmm. Because the next guy is named Giorgio Parisi. He's the Italian dude who won it from the Sapienza University, I think, in Rome, Italy.
Yeah, yeah.
And yeah, he's legit. He's I think they cited like 6 of his papers in the Nobel Prize or something.
Yeah, it says they awarded him for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales.
Right.
Huge.
So basically, he's the big guy on that panel because the other two guys, Manabe and Hasselmann, actually used his mathematics to figure out how to actually quantify climate change properly on Earth.
Damn.
So he is the main guy, I think, in that pool of people. You know, like kind of how the Penrose was the main guy in the last Nobel Prize for physics.
I guess they're doing this whole thing where it's like idea and application.
Right. They're trying something here, like trying to show you that it's not just the last person who wins. It's like there's a lot of people who underpin that discovery.
It's kind of an interesting interplay there of like, there's like somebody who, it's not only is it your idea is impactful in the way that it's executed, I guess. Right. Interesting.
Yeah, but you know, this Parisi guy is pretty interesting because you know he's been in the game for a while. Of course, I think he's one of the older guys on there, if I want to say so. I think maybe
Hasselmann looks like he's got a little bit of gray hairs on him.
I forget who's the young guy on the panel, but there's 2 guys who are born 1950s, I believe, and the other guy was maybe 70s or something. Mm-hmm. But anyway,
well, I mean, I can't tell with the other guy,
Manabe.
Yeah.
Are you trying to say Asian don't crack, or?
Well, I mean, with somebody who's, I mean, just the I think the specific diet is like it lends to looking really young.
Right.
Apparently, they did a study about this, like Asian. I think in Japan, it just scores their diet scores for low in or high in antioxidants or something.
Oh, okay.
But low in like salts and all this other stuff.
Well, those motherfuckers are always eating good, man. In the U.S., we're fucked because we got everything that has sodium and sugar in it. At crazy levels.
And just
I wish I could eat a Japanese diet.
Yeah, and there's just no vegetables in anything.
Right.
Yeah.
But I think Manabe actually is American. Mm-hmm. I don't know if he was born in America, but he definitely works here, so I'm sure he's been here for decades, I would imagine.
Maybe the McDonald's got to him.
Maybe it did.
Unfortunately.
That aged him probably about 10 years.
Yeah, he had one bite of McDouble. He McDoubled in age.
Oh, that's how they got the name. It's pretty good. Anyway. So Giorgio Parisi, he basically is the guy who underpins a lot of this discovery. And again, as I said, it's related to chaotic systems and, you know, complex systems and chaotic stuff. Uh-huh. So trying to quantify chaotic or random systems in some kind of way, which sounds hard as fuck.
Yeah.
And it's crazy because this research actually extends into a lot of areas. Like the examples they gave were that it extends into like neurons.
Right.
You know, the study of neurons, a lot of biology related stuff.
Crazy.
Obviously, because biology always has these crazy amounts of, you know, variables, you know.
And complexity.
Yeah, and complexity. And it's always computationally intensive. So it makes sense that his models would extend there. And he invented this particular technique called the replica symmetry breaking technique. And it's pretty interesting because it entails basically this. It's an interesting technique. So I'll try to describe it. So.
Yeah, dissecting it because like replica symmetry.
Yeah, you're like, what could that possibly be?
So when I think, okay, so you can break down almost every word in that. So like symmetry in itself is something that has uniformity across, right?
Yeah, you could probably spend an hour-long video on just symmetry alone, right?
And then when something breaks symmetry, it's said to, I guess it just looks slightly. I guess what's a good example? Okay, so like if you're driving along the roadside and you see one of those wire fences, right?
Okay.
And then like let's say that you've ever seen a fence that like just shifts, the wires just shift slightly down, and it's like the pattern looks different.
I think.
You know what I mean?
Not exactly.
Because as a kid,
It's a strange example.
It's a strange example. It's the only one I can think of because.
Oh, are you saying when it connects to another fence? And
Yeah,
it's not
yeah,
quite
and
aligned?
yeah, exactly.
Sure, okay,
That's like a good example, like symmetry breaking.
Yeah,
it's like,
yeah.
oh, it's a continuous pattern, and all of a sudden, it's like the pattern changes.
Right.
Yeah.
I think the term symmetry breaking is kind of obvious. Maybe not if you want to go really fine into detail.
Right.
But yeah, symmetry breaking just has to do with basically the symmetry is broken, exactly how it sounds. And I think there's a guy that we're gonna watch a little bit later on named Stephen Blundell.
Shout out.
His video actually has an example of using symmetry breaking as he has this weight on a pole. So like if you imagine imagine a kettlebell on a rod. When the kettlebell and he's
We're gonna.
Yeah.
Oh, we're gonna watch it.
Well, not that
Okay,
particular one.
okay,
The
gotcha.
video's like 50 minutes long.
Oh.
I linked it in the community page a week ago. So if you guys remember that, you can check that post. It should be on there. But he basically has it where you can tune the kettlebell's mass, let's say, and then the mass will eventually have a symmetry breaking effect on the pole because the pole will bend one way or the other. Let's just imagine it's a two-dimensional constraint. The pole is going to buckle one way or the other. And he's saying that buckling is kind of arbitrary because you don't really know if you're trying to keep the kettlebell exactly in the center. A very small deviation will cause it to go either left or right.
Yeah.
And that's an example of symmetry breaking. Of course, we've talked about in the other videos, like I think with Yang Mills, we talked about the Mexican hat potential.
Yeah.
I think you even commented on it. That's a little bit problematic.
Well, I said it was just silly that it would call it Mexican hat out of all things.
Right. But the Mexican hat potential is a classic example people use for symmetry breaking.
Yeah.
So
Just call it a
sombrero.
sombrero.
Well, I think I said I liked the hockey puck.
Hockey puck is actually more billing. It's
Yeah.
more billing for sure. But anyway,
symmetry breaking is exactly how it sounds. It's just the symmetry gets broken.
So when they say like these small deviations, is that how they kind of like try to mathematically model those deviations?
Oh, using perturbation theory or something?
I don't know. Maybe.
I think they do in some instances, but this is not related to Parisi's research, I believe.
His model.
There may be a connection or something. Of course, I'm not an expert. I don't know shit about chaos theory, so take literally everything I'm saying with a grain of salt.
Well, because like his is specifically, what does he call it? Replica.
Replica symmetry breaking, RSB, is the technique.
So it's a different kind of symmetry breaking. He's like, it's a replica symmetry breaking.
So let me just describe the technique. So what they do is there's this example of imagine a two-dimensional square, right? So a square, I guess a two-dimensional square is redundant. Just imagine a square. So there's a square, and you can fit these marbles in the square, let's say, or circles in a square. Let's just imagine that you're pushing a collection of circles in a square to where it fits exactly in the square. Now you can do this multiple times. Let's say you're pushing it at all four corners. This is just the example I saw online. I don't know if this is overly complicated, but I'm just going to use this one because it was very easy for me to understand when I saw the picture. We're going to see if we can actually explain it well too.
Yeah.
But what happens is these circles that are just lying on this two-dimensional plane get all pushed. So it's like a packing factor or a filling factor, like you look at a jar of jelly beans. Like you can arrange a jar of jelly beans with a different packing factor because you don't know exactly how the jelly beans are going to be arranged exactly in that jar, right? Like there's going to be a certain amount of space left over, but every configuration is going to be slightly different from one another. So this is the same kind of scenario, only it's just a two-dimensional version to keep it simpler. So what he does is he makes an exact replica of this model over and over and over and over and over and over again. So he makes numerous iterations. And then what happens is with those iterations, you will eventually see an emergent pattern from those replicated systems. So you pack in those marbles multiple times in each of these squares. And then eventually he's saying that there should be a pattern that emerges from that chaotic process. So you can think of it almost like it reminded me of how we do probabilities. Like with quantum mechanics, the probability distribution always ends up with these single answer values.
Right.
When you do it with enough iterations. So this replica symmetry breaking technique is very similar in that sense that he's packing this square full of these marbles, let's say, and then it reveals some kind of emergent pattern from doing the process so many times over and over again. So it's a pretty cool sounding technique that makes a lot of sense if you just think of it in that way, I think.
That's interesting. So these things are amplified. Like,
yeah, it's like you get some kind of emergent pattern out of this. I don't know if it happens for all systems, but I guess for at least some particular systems it actually works. And then there's some quantifiable pattern that you can actually derive from that process.
I mean, they said from atoms to planetary systems, so
yeah. So it's interesting the amount of things that link up in there in his statistical methods here, because it was even interesting because there was another phenomenon that this is related to that we actually talked about a little bit during our episode on time crystals. So there's these things called spin glasses, which they use this technique for. So spin glasses actually use these chaotic techniques that Parisi has invented, basically, I think to figure out this behavior of these weird particular condensed matter physics objects. So
yeah, like in spin glass is like it's like an exotic phase where something looks like it's in I would just say perpetual motion. It's almost like
you're talking about a time crystal specifically,
right?
Because there's spin glasses that don't necessarily have to be time crystals. I think they call the time crystal pi spin glass. I've seen or something.
Call this pi spin glass,
but spin glasses can be. They actually, let me read it because I got on Wikipedia the particular properties, and they specifically quantify the spin glass using its magnetic properties. So let me just read this. It's from Wikipedia that I found this.
Yeah, go for it.
Let me see.
This one?
Yeah. You want to read it?
Yeah.
So it's under, I think, it's got a nice picture too. We should probably put that on the podcast. It's under magnetic behavior. It's really good. That whole paragraph is actually really good.
Yeah, so
you can read maybe some of it.
Yeah, spin glass, I guess in general, is a magnetic state characterized by randomness besides cooperative behavior and freezing of spins at a temperature called the freezing temperature. And I'm not going to explain what magnetic spins are.
Well, you need to.
Oh, I do? Okay, yeah. Magnetic spins are the orientation of magnetic poles in three-dimensional space. So in like ferromagnets, for instance, the spins align in the same direction.
Right. In a spin glass, they align all randomly oriented.
Yeah.
So read the part that says if in a magnetic field.
So for magnetic behavior... Wait,
this is the important part.
Yeah, I'm going to read the magnetic behavior.
This is really what quantifies a spin glass. The magnetic behavior section is the most important.
So if a magnetic field is applied as the sample is cooled to the transition temperature, magnetization of the sample increases as described by the Curie law. So upon reaching the freezing temperature, the critical temperature, they just wrote TC. Okay, here it's actually, here TC means the transition temperature.
Yeah, so freezing temperature works. It's freezing the magnetic domain or magnetic moment.
The sample becomes a spin glass, and further cooling results in little change in magnetization. This is referred to as the field-cooled magnetization. Now, when the external field is removed, the magnetization of the spin glass falls rapidly to a lower known value as the remnant magnetization.
Yeah, so the remnant magnetization is important here because this is what distinguishes between some of the other magnetic objects. So read that paragraph again. You said it falls what again?
So when it reaches like the transition temperature, the sample becomes a spin glass. So the spins become random.
We'll just read that section again.
So anyway, there's when the magnetic field is removed, the magnetization of the spin glass falls rapidly to a lower value known as a remnant magnetization.
Right.
And the remnant field, I guess maybe they'll explain it here.
Yeah.
Anyway, the magnetization then decays slowly as it approaches zero. This decay is non-exponential, and no simple function can fit the curve of magnetization versus time adequately.
Mm-hmm.
This slow decay is particular to spin glasses. Experimental measurements on the order of days have shown continual changes above the noise level of instrumentation. Spin glasses differ from ferromagnetic materials by the fact that after the external magnetic field is removed from a ferromagnetic substance, the magnetization remains indefinitely at the remnant value.
Mm-hmm.
And paramagnetic materials differ from spin glasses by the fact that after the external magnetic field is removed, the magnetization rapidly falls to zero with no remnant magnetization.
There you go. So that's pretty good. So that's what I wanted to read. So the difference is the ferromagnet, as I said, the remnant magnetization, which is like the remaining magnetization once the field is turned off, remains. And then the paramagnet, the field falls rapidly to zero. So the spin glass, the key property experimentally, is determined by showing that remnant magnetization falls gradually over a days-long period. So it's got this weird gradual drop-off. And that kind of reminded me a little bit of the time crystal. But the time crystal was even more stronger because it didn't even... like there was no gradual decay of anything. It was just like there was this weird non-energetically using periodic state.
There's periodicity.
And if you guys want to watch that video, there's a time crystal video that we did a while ago. I don't know how good it was though, because it was more of an introduction. But anyway, that's just another form of a spin glass. They call it the pi spin glass, I believe, or something along those lines.
I guess the pi means like it's an emphasis for periodic, sort of.
I don't know about that. I don't know. This is out of our element, so I can't really say. And I don't even know if
we don't study spin glasses, and we don't study the only glasses we study are the ones with alcohol in them, folks. No, I'm just kidding. Or the ones on our faces.
Anyway, but the thing is, the spin glass is one of those main areas of study that, or one of those main applications for Parisi's theory. And even stranger related that I discovered from this was that the spin glass mathematics, the statistical mathematics related to spin glasses, is actually also related to neural networks. So neural networks use the same mathematics that Parisi invented for the spin glass. So it's like, man, I get why he got the Nobel Prize, because it's got all this weird crossover. That's another beauty part of physics, is just the fact that you can apply these weird, seemingly unrelated mathematical concepts to other
complex systems.
Other complex systems. So neural networks also uses this weird statistical mathematics.
Damn.
So it's pretty interesting, and I mean I think the list goes on, the applications of this stuff. And of course, like we already mentioned, of course the two guys who won the Nobel has to do with the climate change models. So these complex systems, these chaotic systems, these disordered systems are getting a lot of play now from this Nobel Prize.
Damn.
Yeah. So pretty interesting.
That's crazy. So where does the first? I don't get how. What was the R word that he used?
Replica.
So
that's an important one because he's replicating that model over and over again. So it's an iterative process, basically.
Huh. So what do you think? Do you think there's any crossover between this and maybe what Wolfram is doing?
Oh. So I'm not really sure.
You just said neural network. You just said networks, and I'm like,
right, because networks is how Wolfram built his model. Bro, I don't really know enough to say that. I don't really know how even close Wolfram's stuff would relate to neural networks.
Yeah.
But then again, I'm not really sure. Yeah,
it's like very chaotic and whatnot.
Yeah, you're right. There's like a chaos component to Wolfram stuff.
And you're talking about iterations a lot of the time too with him.
Right.
It's a similar language, it seems like, in some ways.
Yeah, man, who knows? Like, all these systems could have some kind of relation. The first things I thought of when I was thinking of chaos theory is, I always think of the Lorentz attractor, right? The butterfly effect. You know that one?
Lorentz attractor?
Yeah, you never seen that from differential equations in high school? I mean, in college.
High school.
Undergraduate, I'm getting like these fucking professors.
You didn't know calculus in elementary school?
Yeah, you just gave me this like,
Right.
damn, bro. I was like, dang, I didn't know you studied it like that.
No.
Okay, what do they call it?
The Lorenzo tractors. So you probably seen it. It basically is this thing that's like a little. It looks like It looks like butterfly wings because it's in reference a lot of times to the butterfly effect too.
No clue what that is.
I'll put it on the podcast, but I just want to show you one.
I feel like you might recognize it if you see it.
The only thing I have really the only shit that I know. Oh, okay.
Yeah.
There's book covers with it on there all the time.
Yeah, that was
and
on
everything.
a book cover for calculus, probably.
There you go. Yeah.
So the Lorenzo tractor is one of these chaotic systems that, is a classic example of a chaotic system. I was curious to see what the relationship was with that and the spin glass stuff, but I didn't find any. So they might be kind of a different relation, or just maybe I just don't understand it enough to make the connection myself. Or maybe people haven't connected them yet. But, it's just interesting because it does fall within that field of complex systems and dynamical, stochastic systems. But, yeah, I don't know relation. And if there's a commenter on here who does study chaos theory and, these complex dynamical systems, leave a comment by all means of anything that you know of how those might be related or if they're not related. But yeah, it's just interesting. Do you know any other interesting chaotic systems that you can think of?
The only time I was in, speaking of like chaotic stuff, the first time I was introduced to like stochastic methods was in my differential equations class. I think differential equations 2.
Yeah. Okay.
I took it with.
Damn, you took 2?
Yeah.
Wow,
I took it with
over here.
I took it with a professor who this Mexican guy who was like very. He had his own mariachi band. I swear to you, he had his own.
What do you mean?
He had his own mariachi band, and he would like play with his band on the weekends.
Oh, that's what's up.
And he would be like,
"That's
hey,
cool.
I'm gonna go drink with my friend." Like he was like the most Mexican American professor I ever met in my life.
Wow.
He was like,
That's how you got to do it, folks.
You got to keep your life balanced.
He was like, I'm gonna go play with my band, this weekend. He was so cool and chill. Like he was probably the most. He was the most down to earth person. Yeah, I guess he's like, why are you calling it? Just call it a sombrero, man. Nah, but he was, and he legitimately talked like that. Like he wouldn't even like. But it's funny because like when he would talk about math, he would get very serious. But anything outside of that, he's like, I think one of my favorite quotes is attributed to him. He said, "Life is hard." He's like, "Drink a beer."
It's true, man.
And I was just like, man, this guy gets it. This guy gets it for sure. But he studied like stochastic systems. Like one time I asked him like,
So maybe this is related to like his field because
probably
complex systems.
Yeah, I was like, what does that mean? He's like, oh, like you study, you physicists like periodicity and stuff. And he's like, I study the hard stuff. I study the real stuff.
That's true.
And so he was just kind of like shitting on physicists for a good time, but then he was just like, he's like, yeah, I mean, this is like really groundbreaking stuff that I'm working on, but he's like, it's really difficult.
Yeah.
And it's like you need computational. At the time, it was. I mean, you needed a lot of computational power to kind of see any. I guess like what he was saying, like the reproducibility or the iterations that you need to do to even see emergent phenomena come out of.
Right.
Yeah.
Yeah, it's the hard thing about these chaotic systems is they have these. Like you want to just do an iterative process to figure out the answer, but it's like the problem is that the solutions become untenable after a certain degree that you reach. Like, maybe 5 iterations you can do, and that'll get you can do it in like an hour, and then it'll be like, oh, you can do 10 iterations, and that might take you 10 hours, and then you might do 50 iterations that take you to A to G to the universe. So it's like these things scale up really fast to where you can't just do iterations a lot of times, and that's why people are so interested in finding these clever tricks and analytical methods to these kind of problems, because then they might glean insight from these things to where you can actually maybe even set up a problem with ideal situations to where you can get answers from them or some kind of understanding of what's actually happening.
Yeah.
Because I think Stephen Blundell even had a good quote from his video, which we'll watch him in a few, where he was talking about how basically we live in a symmetry broken universe.
I think you saw it when,
Yeah, I
when
saw
you were
it.
eating earlier.
It was very poetic for him. He's like, the universe is he basically made it seem like life sucks, but
I wouldn't take it as that, but
okay, maybe I'm projecting my own.
sad boy one over here.
Life sucks. Anyway, symmetry's cool.
But no, he was basically saying that, the life is symmetry broken.
Yeah.
Like the symmetry state is kind of this idealized perfect state that's not real. Like we live in a symmetry broken life.
World,
so
yeah.
the real problems, all the real problems in life are symmetry broken problems.
Yep.
So when we have the privilege and the the luck to be able to study these symmetries, the perfectly symmetrical situations, these are the kind of unusual states, right? It's like these are like,
But these are the actual, what he's saying.
Well, these are like the tools that we have to use to figure out these real, actually more complex
Problems,
right?
Agreed.
So, we're just trying to work with this small handful of tools to figure out all of reality, which is the symmetry broken state.
The first time I was introduced to chaotic systems, I think, was in my classical mechanics class.
Mm-hmm.
I think. Maybe it was that, or maybe it was in quantum mechanics. I can't remember exactly when, but in depth, it was in grad school for sure.
Yeah.
We were studying a periodically driven motor, but it's like, with like a pendulum or something. It was kicking a pendulum or something.
You just made me think of the rotor problem in quantum mechanics.
Yeah, that is.
I don't know what the fuck that even means anymore.
Well, in classical mechanics, right? The rotor problem.
But didn't we do a rotor in quantum as well? But
Yeah.
wasn't there a
There's
quantum
also
rotor or something.
Yeah, there's
Or
a
am I
quantum.
hallucinating?
There's a quantum rotor, but it's more. I guess it's showing that it's a system that's periodically driven.
Honestly, I don't even know what that means anymore.
It just means something that's periodically driven, like.
But that's just a harmonic oscillator then.
Yeah, but externally, I guess, as opposed to one that has its own internal potential versus an external potential. Meaning, like a field is an external potential, right? That you apply it to the system.
Okay.
As opposed to something like that has its own internal stuff, like
It has an intrinsic
like
field?
something that's like something that that functions like a harmonic oscillator, like a particle in a well or something, right?
No, I don't know. Let's just skip.
Let's get this.
Skip.
Okay, we're getting.
Can I tap out?
You can tap out. It's a little late for this anyway.
Yeah.
So
Let's not say wrong shit.
anyway, what I'm trying to say is that in this classical mechanic problem, they show us they showed us a pendulum, but it was like a chaotic pendulum. So once you went out of
It was like on a cart or something.
something like that.
I remember a pendulum that was on a cart.
Yeah.
So it was moving in this chaotic fashion because
Yeah,
it
you
was
do
like,
get chaotic.
or maybe it was like a
solutions.
periodic cart and then the pendulum was attached to it or something.
So at certain, so you could see the bounds at which the system you could solve the system.
Okay.
But then there were other solutions that you couldn't really
Okay. I don't remember.
ascertain, I guess.
I remember doing some funky pendulum problems in class mech, but I don't remember the extent.
Well, the funkiest one was definitely the only way you could solve it was by using computational methods.
Oh,
So
I don't remember
they
doing
would
that.
so they would show that you would have a phase diagram. So you'd have these phase diagrams, and phase diagrams are like momentum. They're in momentum space, so it's like momentum versus what was it? In this case, for the pendulum, it was angle, but you try to have the most reduced. What is it called? The reduced. I'm trying to think of the name of the term.
What?
Reduced. Like you're trying to reduce to the simplest variable in your system. Do you remember what that was called?
No.
Dang.
Generalized coordinate?
Thank you.
Okay.
Yeah. The most generalized coordinate you can think of possible.
Yeah.
And in this case, it was like, for most pendulum systems, it's literally theta. It's just,
Okay, yeah.
right?
Right.
And
Makes
so,
sense.
you would have this this map, this phase diagram map of the angles and stuff. And then you would see like a bunch of like static essentially. But then you would see some regions in theta that had pockets of like some order to them. Like they would kind of look, you would see like it looked like kind of like what you showed me with Lorentz. What are they called?
The Lorentz tractor.
Yeah,
Okay.
yeah. You saw some of these like weird oval looking things,
Right.
and that showed that there was like order in the chaos.
Mm-hmm.
So like all other areas of the map that were kind of static, they're just chaotic.
Right.
But the parts that were ordered like that, they kind of
So they could extract some kind of pattern from
exactly.
it. Right.
Yeah.
Right. So I guess that's the whole point of chaos. Study of chaotic systems is trying to ascertain any kind of pattern you possibly can from the chaos, which is hard, right? Because random shit's random. So it's like, if you can extract any kind of pattern, that's going to be useful.
Yeah, and the number of iterations are important too.
Yeah, a lot of times it can be.
Yeah, because like when I would input this code on, or whenever I had this like phase diagram thing in Mathematica, it would do. I only put it to 100, but after like there were some solutions that you couldn't see unless you went to a certain higher order of count of iterations.
Right.
So there is stuff to glean from if you go to a certain higher number of iterations. So that is important. Computational power is important. So
yeah.
And
ideally, if we just had a quantum computer, maybe we could just figure all this shit out. I'm just joking. I'm being facetious because I don't really know if a quantum computer can
solve these problems.
These problems, but I'm sure there's probably some. I mean, I'm not sure, but I would imagine there might be some. I don't know.
Yeah, because I mean, they say quantum computers can solve proteins. Those are pretty.
And proteins are related at least to some of the
chaotic systems that Parisi was.
Yeah, because I mean, proteins are fucking wiggling all the time.
Right.
Like, they're hard to. They literally snap into configurations that like almost in an instant where it's like how does this happen? Like we don't understand. We have a hard time understanding macro.
That's right. You got the biology background.
Yeah.
For the audience not familiar, Juan is coming from a biology background, so he randomly knows some shit about biology, and I'm always like, why would you know that?
Okay, I was a really good bio student, okay? But then I realized I'm not going to med school, so what's the point? Let me pick something equally as... Actually, I probably could have cut it for med school.
Could have cut it for med school? I can see it.
Yeah.
But would you want to, is a question?
No.
You can't see yourself doing, like, surgery or something?
A technical surgeon, probably, but...
if you had to pick one,
I wouldn't be doing it for the right reasons.
Oh,
Do you
I
get
see.
what I'm saying?
Yeah, you'd be like, well, I get a lot of money.
I mean, obviously, helping people would make me feel good, but the amount of stress and hours and stuff,
the hours are fucked up.
I'd be like, man, this ain't. Look, I love helping people, but it ain't enough.
Right.
Yeah, it wouldn't be. I mean, helping people is just.
You can do that many ways.
I'm going to cut my tongue here. Because
well, you can help people in a lot of ways.
I can help people in a lot of ways. Yeah.
Yeah, but you could be making 6 figures and, as a surgeon.
I feel like I would really be like Doctor Strange. Kind of like.
Would have powers?
No. No, I would be like him, like in terms of like he's kind of a jerk. Or I'd be like Dr. House kind of type of guy. Where I'd kind of
I don't see that, but.
Or I would be kind of a curmudgeon a little bit.
You think?
To my coworkers, but I wouldn't be a curmudgeon to
your colleagues.
I would be a curmudgeon to my colleagues.
Oh, but not to the patients.
Not to the patients. No. I'm too.
I don't see that though, Juan. I feel like you're too agreeable.
Too agreeable. I guess maybe so, but I would be.
Maybe a curmudgeon on the inside.
No, I think I would joke about hating my job. Probably.
Okay. Yeah.
Do you get what I'm saying?
Yeah.
But then I'd be like, I'm glad to help people, but. But yeah, it's interesting because like proteins are these macromolecules, right? That have, you have a bunch of arrangement of atoms interacting, and some regions you have that are more electronegative than others, so they're pulling like different parts of the molecule. It's
just complicated.
Very complicated.
Yeah, bio shit is just always complicated, guys. So anybody who's watching this who might be like interested in going to biophysics or something, Good luck to you.
Good luck to you, because it's actually harder than traditional physics,
Yeah.
because
Any of these higher level systems with a lot of complexity are just hard as fuck. Like turbulent systems, like Navier-Stokes, one of the classic millennial problems. Like people think that's probably one of the hardest problems on the list, and that's because it has to do with these chaos type systems. Like chaos is just hard as hell to quantify, because the thing is there are so many variables, and the iterations become untenable after small numbers usually. So it's like the creativity you have to have is a lot to be able to try to figure out these things, and the math can be pretty tough. So, of course you like a challenge, and by all means, of course it's good, but
yeah.
I
Well,
would definitely say you should, if you want to go into that field of like chaos systems and that kind of stuff, study a lot of statistical physics. Study, I think the modern framework they use in a lot of things is like mean field theory for some things. Study computational methods would probably really help. If you get real good with computers and understanding how to run simulations and that kind of stuff, programming, computational stuff, I think that'd be very useful. Of course, I imagine linear algebra as well.
Good luck finding a program in physics for that. Honestly, I mean that
Maybe
genuinely.
computational physics. It's a little bit less like of a thing as far as I know, though. But
Yeah, that's kind of why I'm saying that. Good luck, because
but
I don't.
in graduate school, you can make your own degree in some sense.
Right. Yeah.
You just have to know what you're doing, though. Which a lot of times you don't when you're coming in, right?
Yeah, and you'd have to find the right advisor. But I mean,
Yeah.
if you're trying to study chaotic systems, right?
Yeah.
You do need to. You'll probably more than likely find that in the math department. Funny enough, I mean the guy that I
Or maybe
studied
computer
differential
science.
equations, maybe. But I'm saying, like, if you're a physicist right now, here's the thing: we had a physics student that we knew that was trying to study like high theory,
Yeah.
and I'm like, you're not going to find that here in the physics department. You're going
No.
to find that in the math department.
Yeah.
Like,
Yeah, there's certain things that, like the physics standard track is like, condensed matter, nuclear, particle, astronomy. And then if you
Right.
start to get out of that branch, you're going to have to kind of know what you're getting into.
yeah.
Maybe if your
By the way-
advisor does some things, then you might.
Well, by the way, but out of those 4 fields that you said,
Yeah,
those have an experimental route and a theory route.
right.
So,
And there's a million variations you can do on that theme, but it's like,
but those are the main ones, right?
yeah, you kind of got to know where you're going if you want to solve particular problems. If you're interested in chaos theory, you need to like build up your skill sets by understanding kind of what the track is to do that. And then for me, if you want to get into that kind of stuff, I would recommend first off just finding the most relevant books right now, like type in like top or best books in complexity theory or chaotic systems, and then see, in the table of contents what mathematics and things or concepts they talk about, and just look through papers,
Probably stochastic methods.
right, and look for what techniques and things that they actually use, and then see what branches of physics and mathematics those require, and like see, there's statistical methods there, so you got to learn statistical methods, and then see that they use like these Monte Carlo simulations, and you need to learn Monte Carlo stuff. So it's like you can kind of get what you need to get if you start with the modern day framework and then build backwards.
Yeah, for Monte Carlo methods, I really hope that you put a picture of a Monte Carlo car.
Well, maybe I can, when I edit my part, and then you can edit some of it, you can throw that in there.
Yeah, because that was like my first car, the Monte Carlo.
Oh, really?
Yeah. So maybe
you
I'll
like it?
Photoshop a picture of me in a Monte Carlo. Me in high school in a Monte Carlo. That'd be funny.
Was it a good vehicle?
No, it wasn't.
Oh.
They were made by Ford, I believe.
No, I thought Ford made good vehicles. No?
You thought wrong, my friend.
Well, anyway.
Anyway,
And I wonder if people
well,
notice
actually,
the difference between your editing and mine, too, because I usually edit more like literal, and you usually edit more comedic. Although I will do comedic every now and then, and you'll do literal every now and then, but I think we skew towards that.
True, the deviations.
Yeah, maybe we should just combine our editing powers for the full scope of comedy and
comedy and literalness.
Yeah, and literal physics.
I was gonna say, what was? Fuck! Did I lose it?
Oh yeah, my bad.
No, I
Cut you off.
forgot a little. I forgot what I was trying to say. What were you saying before? Maybe you can warm me up.
Monte Carlo.
Thank you.
Yeah.
Monte Carlo. What? So for those
Your car.
no, for those that don't know, can you explain what that is? Do you know?
Oh, I don't really want to get into it because I don't actually have a good explanation for it.
Yeah, but it is like a.
But I guess I can give a very bare
Yeah,
bones
yeah.
explanation.
Just if people want to go look this up because I'm familiar with it, but in passing, really.
Yeah, it's like an iterative process that you can derive certain quantities from. It's like kind of like a simulation that you can run in some sense. Like a Monte Carlo simulation basically allows you to like numerically solve these problems. I don't want to get any more than that because I don't want to say the wrong shit because I didn't actually study it for this podcast to give a nice definition for it. But just type in Monte Carlo, MonteCarlo, or maybe we can even
Put a video in here. I don't know. We'll see.
Yeah,
Maybe
Monte
not.
Carlo. I'll give the official definition here. Monte Carlo simulation, and this is from the IBM website.
yeah.
It's a Monte Carlo method or multiple probability simulation, which is used to estimate the possible outcomes of an uncertain event. And
Yeah, it's very broad.
mathematical technique. But yeah, they basically use it for. It's mostly used to account for risk in quantitative analysis and decision making.
Right. It's a very useful thing to learn. Like if you want to learn a computational technique,
I mean, it's like
a massively useful one. They use it everywhere.
Yeah, I mean, if you're look, here's the thing. For a while, I flirted with the idea of me becoming an actuarian
Oh, really?
because
they make money.
Oh, because by the end of because here's the thing with being an actuarian, it's already laid out for you.
What do you
After a
mean?
certain number of, because they have their own levels. It's like
Oh.
5 levels.
Okay.
So the first level, if you pass that test,
This is like Scientology.
no, and actuarians like they study chaotic systems. I guess
Yeah, yeah.
they do a lot of stochastic methods because they end up working for insurance companies and
Yeah. They're just trying to
what was I
calculate
saying?
risk and things.
probability.
Like that.
Yeah, risk and probability. And so your first level, yeah,
It's gonna show up on the audio.
God, I've been clicking that shit the whole fucking time. Anyway, I'm sorry. Carry on.
God damn it, man.
anyway,
High budget podcast. Everybody.
it's just the microphone cable. I don't know what the hell's wrong with it. Yeah, please, chaotic theory. Please explain why shit gets tangled up like this. It's so ridiculous. Anyway,
Monte Carlo.
yeah. Well, being an
Actuary.
actuarian, like there are like 5 levels or something, and if you pass the first level, you're like guaranteed 100. Like I think it's like 100K you start making.
Yeah, that sounds
Almost
about
right away.
I know it's like a lot of money off the bat.
And if you get to level 4 or 5 or whatever it is, it's like you make $500,000 a year.
Damn.
And as long as you pass those,
Mm-hmm.
you know, I think there's no real timeline. You can pass them like every 6 months. I think
Okay.
there's like a limit that you can pass each test. But once you get to level 5, it's like the base salary is like
Crazy.
$500,000 a year. It's insane.
Not bad.
And this is just for knowing math,
Yeah.
probability and statistics, stochastic methods. Yeah.
Well, there you go,
So-
guys. You want to get rich?
That's one way to. I'm
Yeah.
saying this as a way to translate this because they do use Monte Carlo methods in a lot of mathematical
Yeah.
stuff.
Yeah, if you're trying to go computational physics, definitely hop on that Monte Carlo train because
Monte
That'll
Carlo
serve you
money,
well.
man.
for sure.
Yeah. Well, you don't want the Monte Carlo money I had, but you'll have different Monte Carlo money for sure.
Yeah, but anyway, I want to jump back a little
Oh,
bit
yeah,
more
yeah,
before
'cause
we get. Let's show that video at least because I know it's kind of a little bit of a diversion, but back to the Parisi stuff. I wanted to just show an example of one of the frustrated systems that they.
Damn, this kind of feels like ham-fisted, but
Why? Well, because
Just kind of randomly comes
Well,
back.
how does it connect to the what Giorgio here was studying?
Well, I guess it was just showing. I guess I didn't really get to it, but I wanted to just touch on it because there's this phenomenon that happens in a particular system. Like if you remember the Ising model, where we studied
Yes.
incandescent matter, right? It's just to explain for the viewers, the Ising model is just basically this lattice of magnetic moments. So if you imagine a lattice of bar magnets,
just small, tiny barb magnets. You can replace the barb magnet with electrons, let's say, or protons or whatever, something with intrinsic magnetic spin. What happens is this Ising model can be reduced down to this very simple lattice, a triangular lattice they call it, to exhibit this property called frustration. And this frustrated state is something that exists in the study of complex systems because it has this chaotic effect where if you imagine the barb magnets, you can have a barb magnet aligned with the North Pole facing up in one vertex, let's say, and then you can say the North Pole's facing down in another vertex. In that other vertex in the triangle, it's going to be in an in-between state because the barb magnet wants to align with the lowest energy configuration. So it's in a state called frustration, and it doesn't know where to line up. So I wanted to just play the Stephen Blundell video because he does such a good job on this entire lecture. And I just wanted to show one part, at least, of the lecture that talked about this because he explains magnetic frustration pretty well.
Yeah, this video does now deserve 5,000 views.
Yeah.
Deserves way more views than that.
Yeah, it does. I mean, it's a really good ass video.
Yeah.
But anyway.
Anyway, here it is. Let me make sure.
Yeah, this is Stephen Blundell.
Symmetry breaking and magnetism.
Right.
An OUPS lecture, for those of you that want to find it.
And it's also on our community page, so if you follow our community page, I posted it a week ago.
All right, here we go.
Same thing with a triangle of spins. First of all, I'll just remind you of something that is rather interesting about a triangle. If you have antiferromagnetic interactions for nearest neighbours, then if this is up and this one's down, you've got a problem on the third spin. Because if you're trying to make all the interactions satisfying their energy considerations, you have a real problem with this third spin. If you did it on a square, it would be easy. You could have the first corner up, down, up, down. But on a triangle, you have something called magnetic frustration. This is the famous love triangle, of course, when A loves B and B loves C, but C doesn't, there's half a dozen movies per year from Hollywood are based on that principle. Now, it turns out classically there is a solution to this problem, and it's one of compromise. Frustration is all about various people not agreeing, and then you have to come to some kind of compromise. And so if each neighbouring bond wants to be anti-parallel to save energy, one thing you can do is share the pain, and that's what happens in most negotiations. So what you can get is the so-called 120-degree state, where the angle between each of that spin and this spin is 120 degrees and this sort of thing. Now, in fact, you could wind round the triangle in two different ways. So the interesting thing about these solutions is that they have two different chiralities. You can wind round one way and have 120 degrees, or you can wind round and do minus 120 degrees between the different spins. And more than that, you can also do a global rotation. So you can rotate all of the spins by a certain angle, and you still have the same solution. So this is true for classical spins. What happens if we go to quantum mechanics? So remember we did this problem, adding a half and a half. If you add a half and a half and a half, the answer is a half, half, and 3 halves. And again, for those of you that have done some quantum mechanics, let me just remind you how you can argue this. 0 plus a half gives you a half, and 1 plus a half gives you half and 3 halves. That's where it comes from. And if you want it in terms of the representations, then 3 spinor halves gives you something with dimension 8.
Okay,
and the dimension of half and a half.
I think that's a little extra.
Yeah.
I guess I just wanted to show the Ising model. It's a little bit of a non sequitur, a little bit, I feel like, but it just was a nice little example, I guess, of the triangular Ising model that I liked to show magnetic frustration. Just another example of this simple problem that you can. I don't know if you can solve it.
Yeah, that got shown as one of the things that it would help solve.
Yeah, I believe. Now I'm like kind of a little bit hazy on why I picked it.
No, yeah, because that actually I remember reading about that because people were saying that it helps solve this problem in condensed matter.
Okay, I'm not sure. Let's not quote that. Let's put an asterisk by it. But I think it had a relation. I don't remember how.
What can you give me?
But if you type in triangular Ising model or magnetic frustration Ising model or something, there should be something that pops up. But the icing model is another classic problem that you can, for
Here we
sure know in condensed matter. Or classic model, I should say, not a problem.
So this one in this article on the conversion, I guess, this grad student that works for Giorgio says, a stepping stone for modeling complex systems is a series of disordered systems. These are essentially systems in which different pairs of elements experience different, potentially conflicting forces that can lead to elements to become frustrated.
Yep.
A way of illustrating this is to imagine a party where Alice may want to chat with Bob, and Bob may want to chat with Charlie, but Charlie may not want to chat with Alice. There's frustration, so what should they do? And
this is
a good
referencing
example.
the three vertices on the triangle, just
Right.
like Blundell was talking about with the love triangle.
Yeah, and so with frustration, when one spin points upward and the other downward, the third cannot satisfy both at the same time because the neighboring spins want to point different directions, right?
Mm-hmm.
So how did the spins find an optimal orientation? Giorgio Parisi's, his results would help answer this.
Does it say specifically what?
Yes, his research clarified what happens when frustration occurs in disordered and complex system. He identified that complex systems are able to remember their trajectories over time and can get stuck in suboptimal states for a long time. So you can, I guess that's what his point was. So in our party example, you imagine Alice, Bob, and Charlie and the other guests irregularly changing conversational groups and partners, hoping to find the best group of people to chat with, yet potentially never finding it. And that's the suboptimal state complex systems can be in.
Right. I guess this has to do with that remnant state in spin glass.
Mm-hmm.
I'm guessing that's a big asterisk again, but I think it's related.
Yeah. Because it says one of the theoretical tools Parisi used to establish his theory was the replica trick.
Yeah.
And just see how many different replicas of the system behave.
And then extract that pattern from the iteration.
Yep.
Okay. Sweet.
So in a similar way, the frustration thing happens too, because, and I imagine society does function like this in a lot of ways too, like how they're giving with the
What do you
three
mean?
people, Alice, Bob, and Charlie.
Uh-huh.
Like just imagine trying to find a good dancing partner.
Okay.
It's a frustrated system because it's like you're trying to find the orientation that matches with you.
Right.
And
Or
it's
dating.
Or dating. You can have a lot of
That's really a topical one I think
s-
everyone can relate to.
a suboptimal, because it is an optimization problem, but it's like you can get stuck in a suboptimal, like I was saying, state for a very long time.
Until the relationship decays to zero.
Yeah, physics in the language of relationships in the language of physics.
Who says physics couldn't teach you about relationships?
Sorry, honey, I'm in a suboptimal state.
I'm going to have to break our symmetry.
Our symmetry vows are being broken. Anyway, is it? Yeah, I know. It's late. But was there anything in particular that you thought was just blew your mind? I guess this is kind of a first take on this.
Well, the replica symmetry breaking was the one that kind of blew my mind because I was pretty unfamiliar with this complex system stuff. Like disordered systems are not a thing that I'm very used to looking into. Like I'm a simple man. I like problems with
periodicity.
Yeah, periodicity,
symmetry.
Yeah, we don't do them disordered systems around here.
We don't.
That's fancy. Higher learning stuff for smart guys.
Yeah, that's literally physicists are literally we're in the game of
simplicity, man. I like my electron to always be the same charge. I like my icing models to be simple. I like these frustrated systems.
I like my fermions to be fermions and my bosons to be bosons. Okay, we don't mix those states ever. Anyway,
yeah. So I mean, are you at all familiar with these complex systems, or were you?
Yeah. I mean, like just talking to that professor, I knew that was a there was another level to
Yeah.
complex. Like physics was kind of like, and this is physicists use like, oh, we make toy models of things, and we really do. We don't really play with the real toys, the Tonka
Yeah.
trucks out there, you know.
We would if we could, but I don't think we can handle it.
Yeah, we're not ready for that jelly, man.
Yeah.
We're just not.
Yeah. It's
kinda-
tough stuff. It's tough stuff. I mean, if that's something of interest to you, I mean, I hope the Nobel Prize gave some more exposure to people, you know.
Well,
in
let's
this
explain,
field and-
but let's explain why it's hard, because like in physics, I know physics is like marred to be a really difficult subject,
Yeah.
but we do.
But the trick is actually it's really easy because we have variables that are consistently the same.
Right, like we deal with things that, I mean, Newton's laws, like it just showed force equals mass times acceleration.
Right.
Acceleration is the second derivative.
Yep.
And like
It's simple,
it's
man.
differential
It's simple.
equations. Like
That's the thing is people don't understand, like people who are like bio majors, like, oh, physics is so hard. I don't like math. And I'm like, you guys are actually doing the hard shit. At the end of the day, you're going to find that out. The farther you go in biology or the farther you go in chemistry, it's just going to get harder and harder because it's
Yeah.
like those systems are complex systems. Like complex systems are always going to be harder because the number of variables you have to account for is just, it's a
Yeah.
lot.
Yep.
And it's hard to extract sometimes the idealized version of these systems because sometimes it's just not obvious.
Yeah.
Like, yeah, I mean, I don't know what else to say. It's just like any higher order systems are going to be difficult.
Yeah. What do you think the implications are for this? Because I can already think of, like you said, the protein one was one of them that might be.
Yeah, they said like neuronal stuff, proteins,
This is going to
neural
change medicine,
networks.
in my opinion.
Well, this stuff has been around already. I think they're just recognizing him now for the Nobel Prize because I think he came out with the replica symmetry
theory.
breaking thing in like the 70s or something.
Really?
Yeah, or maybe the 80s. It's either 70s or 80s. I can't remember exactly. But it's been around. It's just like he's finally gotten his due in some sense.
Damn.
But yeah, I mean, these things are really crucial. I think mostly it has to do with the application. Just it keeps finding new application. Like I think the nail on the head was the fact that it found the climate change application lately, because that's such a relevant issue for these days. Because
We're on the brink of extinction.
yeah, exactly. It's like it's coming. So I mean, it's kind of important right now.
Yeah. Damn. Yeah, but I mean, like medicine alone, like if it solves the problem of protein folding, like that means like we could help. Like medicine would just be taken to another, like a new era.
I don't know if it's going to solve the protein folding problem. I
No,
mean, we
no.
saw a little bit of that stuff with the Alpha Zero, if you remember that. We did
Yeah.
a podcast on that back in the day.
Yeah.
Where there was a computational technique that they used. I don't know if that had to do with deep learning or neural networks, because if it did, then that is related to Parisi
To
again.
replicate, yeah.
So maybe it could, but I'm not entirely sure if that is
Those two are
related to
connected.
those, right? Because there's different types of neural network deep learning stuff. There's
Right.
there's a handful of different models, and I don't know if they're all related to that same methodology. If you're into that space, let us know for sure. But
Yeah, please let us know in the comments, like if there's a deep dive in one particular thing, like how it applies to neural networks, or
right,
Like,
yeah, we're interested to know. I mean,
yeah,
because this stuff is literally the future right now. I mean, this is highly relevant.
Or maybe we could go more into like chaotic systems or something, or Monte
Maybe.
Carlo stuff.
Who knows? We got a lot of shit to go over. We got
unpack.
topics for days, bro.
We do. But anyway, folks, with that, make sure you like, comment, share, subscribe.
Indeed. Check out the websites, Eigenbros.com, Eigenbros on Instagram, Eigenbros Twitter, Eigenbros2 on TikTok. And then patrons, guys, we appreciate you once again.
Thank you.
You guys are making it happen, doing big things here. We're going to try to, and also, guys, you got some suggestions for us to do anything interesting, by all means, let us know.
The
Now that we're
landline
getting
is
some
open.
Patreon money, we're going to try to use it for some cool stuff. Hopefully, at some point, me and Juan got to get our schedules,
Yeah.
more aligned. But
Yes, sir.
we're going to try to figure things out. And if you guys want to join the Patreon, it's patreon.com/Eigenbros. We got a 30-minute audio podcast there every week. Just $1 is all you got to donate. We want to try to get 4,000 patrons.
Jesus.
Is that a stupid number? Let's go for 2,000 for now.
2,000?
That's still a quite ambitious number.
It is quite ambitious.
But if you guys just do 2,000 patrons for $1, me and Juan will quit our
wow,
jobs.
we'll quit our jobs.
We'll do it.
content.
Call in
all day.
Actually, I won't even answer my supervisor's phone. I'll ghost I'll ghost my job. Anyway.
Right.
No, I'm just kidding. I won't do that. But
I would.
I might need that in case the patrons decide to.
Oh, true. Just because they all just canceled their subscriptions the day before.
Anyway.
That would just be mean.
Yeah. Anyway, folks, thank you. And don't forget to like, comment, share, subscribe, especially the share. So,
Yes, indeed.
and we'll talk to you later.
Alrighty, guys. Ta-ta.
Peace.